As we get set up for the next panel, it's the ever-important scientific update on the climate crisis itself. And it's an evolving science. A number of reports, as you know, have come out over the last several years, essentially saying we have really got to step up this great transition. Lester Brown brought us some good news on the transition in wind and solar and declared that over the next decade it will become the dominant energy source for this planet and this civilization. And that's of great consequence. I'm going to let Cindy introduce the panelists and the subject, and we're going to jump right into the reality check on the climate science. Cindy?
Thanks so much. Instead of just listening and instead of me asking questions of the panelists, at the end of their presentations, I want you to do the asking. I want you to be thinking of questions during their presentations. So please write those down and be ready to engage in conversation at the end of the presentations. So my name's Cindy Schmidt, and I'm with the University Corporation for Atmospheric Research and the United Nations Foundation. And those are two institutions that are funding my project, which I would like to plug because I think it could be a good resource for all of you. It's called Climate Voices. The website is climatevoices.org. And this is a network of scientists across the country in all 50 states that are going to their local communities and are willing to talk to any group within those local communities about climate science, about climate change in those communities, and about what can be done in the community. And these scientists are ready to involve with their fellow citizens there. So please go to climatevoices.org and take a look at that developing and growing project. So this morning I am delighted to be here with three distinguished scientists. We're talking about climate science and the current state of knowledge of climate science. And as you all know, it's not just the atmosphere that we're worried about. This is a real sort of jigsaw puzzle of land, water, atmosphere, and two of our presenters this morning are going to address the state of knowledge of that science. And then our final presenter will talk about a possible solution that addresses all of those, the land, water, and atmosphere. So we'll get started on that. Greg Holland is going to be our first speaker. He's a senior scientist at the National Center for Atmospheric Research in Boulder, and his academic career is in tropical meteorology with a focus on weather and climate extremes and the relationship between the two. And you'll hear from his accent that he probably is not from Brooklyn. Susan Avery is going to be our second speaker. She is president and director of the Woods Hole Oceanographic Institution, and we are lucky enough to have her on two panels. She was on one yesterday. Some of you may have heard her then. The Woods Hole Oceanographic Institution is affectionately known as WHOI. And Susan used to work at the University of Colorado as an administrator and faculty member, and then also at the Cooperative Institute for Research in Environmental Sciences, which she directed in Boulder. And those of us in Boulder who worked with her were very sorry when WHOI stole her to go to the Cape. Dennis Bushnell is going to be our final speaker. He's the chief scientist for NASA Langley Research Center, where he's responsible for oversight program for the formulation for several technological areas. And Dennis holds several patents for various inventions and has contributed much scholarly work on the area of biofuels and biomass as petroleum replacements, which he'll be addressing today. Now, please remember to think of those questions, and we'll start off with Greg.
Thanks, Cindy. Can I have the slide? So you can see the title up the back there, and I don't think I'm going to be able to live up to Cindy's expectations, because I don't think I can give you a summary of the state of the science in the next 5 or 10 minutes. We'll just go to Susan. But yeah. But what I would like to do is make 3 points, and those 3 points are: firstly, what actually is climate change? And the second point is, how are extreme weather and climate systems responding to that climate change? Because at the end of the day, it's the extremes that really matter. And thirdly, how can we actually work with society at large, and how does working with society at large help both not fix, but actually let us adjust to and become more resilient to those changes, but also to actually let the scientists understand how they can actually do their job better. So to start with the first one, which is climate change, if you look at the IPCC, and indeed you look at most newspapers and things like that, you see this lovely curve that goes up at a steady linear basis until about now, then it starts to go off like this. And that's only partly true, because if you look at the carbon dioxide in the air, which is the main greenhouse gas that is changing due to us, it's going up like that. But the warming did not go up like that, because up till about the 1960s, we were putting another gas and aerosols into the air, and that was called sulfates. Remember, for those of you with the same colour hair as I have, you can remember the smokestacks and acid rain and all the major ecological problems we were sorting out then. That's what was doing. Now, we cleaned that up. And what had happened before then was that those sulfates are a net cooler, and you have a net warmer and a net cooler, and they were to some extent, indeed largely, cancelling each other out. So the warming that we're actually seeing is because we cleaned up the smokestacks. And it's now accelerated quite rapidly up at a much steeper curve than you see in the simple linear curves. So when I talk about climate change, that's what I'm actually speaking about. With regard to extremes, there is a lot of problems with actually understanding and being able to predict what happens to extremes for one very simple reason. They don't happen very often. And so there's a big noise level. It's very hard to get a statistical signal. But there are some fundamentals that you just can't get away from, and that is if you make any changes to the overall distribution, the means and the way the distribution looks, the biggest change is always at the extreme. So it's not that the changes are not going to be big, we just need to be able to identify them and tie them down better. And there's another story to this as well, because those extremes actually have other limitations other than climate change. For example, the most extreme thing that can happen is usually happen because it's basically used up all the energy there is. You can drive your car maybe 500 miles, maybe 600 miles, but at about 700 miles, you ain't going to drive anymore unless you put more fuel in it, because you've used up all the energy. The atmosphere works just like that. And if we look at hurricanes to start with, this is what has happened with hurricanes. The bottom curve, axis is the number of categories, where category 1, 2, 3, 4, and 5 I'm sure you're aware of, and 0 is tropical storms. And up on the other curve is the proportion of those relative to all hurricanes, so relative to all hurricanes. And if you just focus on the little area out on your right-hand side here, back in the 60s and 70s, when we cleaned up the smokestacks, we had a curve that came down like this. Every decade since then, it has actually bulged up, forming this bimodal distribution. And you can see there's been a bit of an increase out in the Category 5 area, but the big difference has happened at the Category 4s. And that's because the energy limit has changed a little bit, but not fast, but the capacity to intensify has gone up very rapidly. This is all published information. So it's not that we're going to have super hurricanes. That's the good news. The bad news is we've now got twice as many, going on to 2.5 times as many Category 4 and 5 hurricanes as we had before. And it happens globally. That's the global results. It also happens to have happened in every ocean basin except the East Pacific. So that's something we're living with now. Let's look at temperatures. As Cindy said, I'm not from Brooklyn. I'm from this deep south country down here. And in 2013, we had a horrific summer where January actually was the hottest we've ever seen. Indeed, there were several days in January where the temperature exceeded 40 degrees Celsius for the average for the whole country, not just at one station. And there's a lot of talking about it and everything else, so we decided we'd go and have a look at it. And it's actually interesting because this is the temperatures, in this particular case, on one day. The really high temperatures you can see, greater than 42 degrees Celsius. You can see the cooler temperatures around the coast and things like that. Where do you think the records were set? Well, we can do this two ways. I'm going to show you another slide and say, what happens if I apply another 100% of greenhouse? In other words, I double the greenhouse for that situation. What do you think will happen? Well, here's what happened if I double the greenhouse. This is the change. And you can see we've got around 3 degrees Celsius change in those red areas across the country. And I guess I can't go back. I won't go back. But if you remember, the area was there originally. All the hot was up in the center of the country. All of the change is down here. Thank you. And that's because what's happened is the extreme temperatures haven't gone up, but the temperatures near to the extreme have gone up substantially in frequency, same as is happening with a hurricane. And this is also an energetic limitation. It's really hard to get extremes higher. And there's not enough heating in greenhouse warming to do that. So what we've seen happen is this. And you see some unintended consequences here. Look a little bit further north. It's actually maybe a little bit hotter, maybe a bit cooler, but it's mostly nothing or a little bit cooler. The bit down in the southwest is just because of a particular peculiarity that month. But this is something I hadn't thought about, and that is that if the continent as a total is warming up, the summer monsoon gets more intense, and you're bringing more cold tropical air, cold and wet tropical air down into the northern region. These are the sorts of uncertainties you read about in the paper, and people say, well, look, you don't know anything. The answer is we can say sensible things about this. So that's my second message. My third message goes to how we can actually interact with folks like you. And in particular, we're interacting with several groups, and I'll mention them in a second. But I want to show you a slide. Here's a slide. It's an old slide, deliberately so. And you look at it, you can say, well, that was pretty well a disaster. It's not hard to look at that and say there's been something really bad happened there. What do you think it was? Well, here's a headline that goes with that slide. A bloody great tank of molasses blew up and actually took out the entire town in the nearby, entire wharf, sorry, in the nearby area. And my point here is that if we're going to actually say what's happening with climate change, there is another element to the case, and that is that we can't just be building buildings that are more rigid, more extreme, more able to go another 100 years without falling over, because they will. And they will for a whole bunch of reasons we don't understand. So we've been working with groups such as these, the Engineering for Climate Extremes Partnership and Rising Voices. You heard about Rising Voices from my colleagues in the Native American community yesterday. And what we're doing is we're just trying to get a dialogue going where we can actually say, hey, this is what's happening, and we need to actually work out how we can work with you. And I'm going to give you one example which goes back to the picture above that's come out of that, which really makes a big difference to how I do science, but it's making a big difference to how people do planning as well, and that is the concept of graceful failure. We're no longer talking about 100-year return periods for a building. We're still talking about it, but we're no longer focusing entirely on that. We're saying, what happens if the building falls down or the dam breaks? Or the vat of molasses blows up. And what you do is you build the consequences and the recovery from that into the planning process. So you say, if it happens, here is what we need to have as part of the planning process to make sure that we can recover quickly. And that's what I'd call resilience. It's becoming a bit of a buzzword now, and I'm sure you'll start to hear a lot about it. But I want to go a little bit further since we're actually here and we're talking about alternative energy. I absolutely and utterly support alternative energies, and we have to go to renewables. Let me start by saying that. But it is not a panacea. Indeed, there is no doubt that if we took all of our current energy requirements and the growing energy requirements of India and China and the rest of the world, but they're the two big gorillas on the block, and turn them all into alternative energies in the sense of wind and solar power, we will make permanent and unknown at this point changes to the climate. It won't be necessarily global, it may be global, but it'll certainly be regional. A good example I gave you earlier on was when we cleaned up the smokestacks, we did it for very good reasons. We then accelerated the warming, which brings us to this meeting here. When let's say we just simply took all of the energy for the United States and used wind farms to do it. You can't take that much energy out of the wind systems of the world and not make some changes. And it's not just going to happen in the United States, it'll make changes elsewhere. If we make the entire Sahara Desert green to buy our energy or grow trees or whatever we decide to do there, it will change the climate of the world, and it has. There is an example because the Nile Valley was once a very fertile region. It dried up, and that happened in conjunction with the onset of the Indian summer monsoon. So Cindy's given me a wrap-up here, and all I want to do is just simply say the 3 points I hope you'll go away with are, firstly, look carefully at what you mean by climate change or what is meant by climate change. Extremes are going to happen, and in my view have already happened, and I showed you an example. And thirdly, let's keep the dialogue up in a two-way sense, because I think there really will be good things like grace for failure come out of it. Thank you.
Thank you, Greg. And I think Greg really set the stage for what I want to share with you. And again, I think, do I have the power to start this? I guess you do.
I think they said it.
What I want to do is talk about the fact that this climate system, this jigsaw puzzle that was alluded to, has more components to it than the atmosphere. And a lot of times there's the total focus on what's happening in the atmosphere, not realizing it's an atmosphere, ocean, land, humanity process that's going on here. And so I want to talk about primarily some of these intersections of these complex things: sea level rise, what's happening in the Arctic, and the triple whammy of what's happening in the ocean in terms of a warming ocean, acidification, and the increase of dead zones in the ocean and what those impacts are. This triple whammy, is affectionately called in the popular vernacular as the warming, souring, and gasping of the ocean. So I'm showing this slide again because I showed it yesterday and several people wanted to see it once more. Because lots of times when you look at the planet from space, you see all of this water and you think, oh, it's not going to do anything. It's not going to change. I don't need to worry about it. But in reality, as you drain all of this water off the planet, the amount of water that you really have, that really is a major part of our planetary system, is quite small compared to the volume of the planet itself. The amount of fresh water you have is that second dot there that's drained off of the larger blue. And then the smaller dot is the amount of available fresh water. So since the next panel is really talking about fresh water, I thought I would show this again to really give you a perspective of how precious this ocean is and the water that we have on this particular planet. And it is a critical component of the climate system because the ocean is the flywheel of the climate system. It's the memory of the climate system. It basically holds so much of the capacity of heat. And in fact, I'm going to show you a slide later on here that shows that most of the heat, the excess heat that has gone into the atmosphere as a result of excess carbon dioxide, is being taken up by the ocean. Let's start first with sea level rise. And I wanted to focus our attention on the West Antarctic ice sheets and glaciers, because this is some of the latest science that's coming through is what's happening in Antarctica in terms of the melting of the ice sheets up there. And this is an animation I'm going to show, and it goes very quickly. It was produced by NASA, and West Antarctica is mostly covered by ice. Most of that ice is well above sea level rise. But recent work that shows basically that the ice that's feeding into and flowing out of the West Antarctic outlet glaciers is actually speeding up. And so what I'm going to show you here is this animation of that process of the flow coming in and the flow coming out, and it's color-coded. And the red in this color-coded animation basically means faster glacier flows that are happening. So if we go to that, can I do that? Here's your Western Antarctica. We're zooming in. There you see the inlets there that are coming in, and then the outlets of the glaciers that are flowing out. So glaciers are basically rivers of ice that are happening here. So what science is basically showing us what's happening here? Well, what's happening here is that this warmer water that's happening in the Antarctic is basically coming underneath the floating ice shoals that you see here. And as it comes under, it went a little bit too fast here, as it comes under these ice, it puts up and erodes the grounding point of the glacier that basically grounds the glacier in place. So as it erodes this grounding point, the grounding point basically moves landward to Antarctica, and that unstabilizes. It's not as secure. And then the glacier begins to just fall and surge forward and out into the ocean. So this is the process of this complex interaction between a warming ocean and its ice that is basically cascading and melting and putting ice into the water and eventually melting the ice. Now, the amount of sea level rise that could be attributed to a melting of the Western Antarctic is just estimated to about 10 feet of sea level rise, perhaps a little bit more. So what does that mean, 10 feet of sea level rise? Well, let's put it in the context of New York. Okay, so this is New York City with 10 feet of sea level rise imposed on it. And I think the first thing you can see is that you've completely inundated 3 metropolitan airports. Okay? Now, 10 feet of sea level rise might occur over 100 years or so. There's some estimates of that. But in the short term, 10 feet of seawater inundated New York has happened, and it already has happened. It happened with Sandy. Sandy basically was a combination of sort of the small amounts of sea level rise that we have already, combined with a storm at a relatively high tide period that gave you 2.5-foot surge, storm surge, that inundated Manhattan. And that's basically, so these things can happen, this intersection of what's happening on a longer-term time scale to our climate system, along with these extreme events that one is seeing in terms of weather patterns, can easily produce surges like this that we're going to see on a short term. So the point is not only are we going to need to worry about mitigating, and clearly climate science is telling us get off as fossil fuel as much as possible, but there's also an adaptation strategy, and that's what Greg talked about a little bit on his work in terms of the engineering infrastructure of our cities and our built infrastructure that we have here. Adaptation strategies are just, you can retreat. So can we retreat New York? I don't know where it's going to go, maybe to Colorado. We can accommodate. We can raise these cities. Certainly in the 1800s, we raised Chicago, we raised Seattle, but heck, it was a lot easier to do it in those days than it is today. Or you can protect. And there's a lot of debate on how do you protect? Do you protect with hardened infrastructure, building walls and seawalls, or do you protect with putting our soft defenses back into place? Putting back, no longer building on barrier islands, putting back and restoring our mangroves, looking at restoring of wetlands. So in reality, there's a lot of discussion going on in coastal communities about exactly how they're going to approach this problem of a combination of both soft strategies to adapt as well as hardened strategies to adapt. So let me go to the Arctic. The loss of sea ice is certainly a sentinel feature of climate change in the Arctic. You've seen this graph before. If you were here yesterday, Sylvia Earle showed the Arctic sea ice area. But the point is, it's not just the sea ice area that's important, it's the volume of the sea ice. And increasingly, what we're seeing in the Arctic is much, much less long-lived ice, age-old ice, 4 to 5-year-old ice, and almost all of the ice is becoming single-year ice, which melts rather quickly. Now, there's an uptick in 2013 here, but you know, this is an anomaly. You see a lot of wiggles there, and the point is that uptick may have increased the area of ice for that year 2013, but it is still 1-year ice. Now, Arctic ice has an interesting, let me stop a minute. This is basically a tipping point with respect to geopolitical issues. But what does it mean basically in opening up the Arctic? Opening up the Arctic certainly has a lot of economic potential. It has an economic potential in terms of fisheries, in terms of shipping lanes, in terms of oil and gas and other mineral years when oils go shedling. Got to come response getting an area to help rise difficult visibility and how important strategy as this area. Consequently, particular aspects of an opening Arctic and the economic values that they have. Interestingly enough, the boundary lines between the US and Russia have been well established as a result of the Cold War. Okay, but it's the other nations that are still arguing what's going on here. Finally, I'm going to skip this. Just go to the triple whammy. And that is that as carbon dioxide increases, that carbon dioxide in the atmosphere is dissolved, part of it dissolved in that at the P, and you have consequences the whole system. Research now that's really looking at the biological functioning and the relationship between pH conditions and healthy ecosystems. And clearly, one of the problem areas is the habitat loss associated in our coral reef systems and the production of mollusks, their ability to thrive and biologically function. So that is the acidification issue. The warming issue, okay? The ocean is warming, okay? And most of that heat content is in the ocean. So this just shows you the fact that the ocean, the heating that we have from the carbon dioxide, increased carbon dioxide, is ending up most in the ocean. If we didn't have an ocean, there'd be a heck of a lot more atmospheric heating right now, okay? So without that ocean, okay, that ocean is buffering us right now. But as that ocean continues to warm, it has significant consequences. And this is my last slide, and it is the growing oxygen minimum zones in the ocean. And let me kind of take it through this with you. First, as the surface ocean is absorbing more heat, it's warming up, okay? And as it warms up, the warmer layer there, if you can see it, The warmer layer basically reduces the mixing of oxygen. So you don't have as much oxygen mixing, which means you're not getting as much oxygen down into the deeper parts of the ocean, which is pretty critical because that deeper part of the ocean is disassociated with the atmosphere. So the only way the lower levels of the ocean are going to get oxygen is through this mixing process. But because warmer water inhibits that mixing process, you're basically enhancing, see, these ocean minimum zones in the deep ocean, and they're going to spread. Now that has tremendous implications for marine mammals that require oxygen, such as the tuna, okay? The tuna really requires oxygen. They live in the deeper parts of the ocean. Without that oxygen, they're going to run into some bits of troubles here. It does, though, provide wonderful habitat for jellyfish. Okay, so if you want to have a diet of jellyfish, we may have lots of jellyfish, okay? Because jellyfish thrive on, don't need the oxygen. Now, this compounds what we're having on coast with nutrient loading from atmospheric deposition and basically runoff of nitrogen fertilizers, your fire retardants, your pharmaceuticals, whatever, in our coastal regions that basically cause phytoplankton to bloom, but phytoplankton basically decrease or pull the oxygen out of our coastal waters there. So as you have these minimum zones increasing in the deep ocean coming up into areas of coastal area where you already have additional stresses associated with nutrient loading, you enhance the dead zones in the ocean increasing. And we are seeing this as well. So what you're having is these complex feedback systems and the complexity of an ocean-land atmosphere system of which science is really beginning to really become to grips with. And we're at a stage where I think it's very important to really make that investment in R&D that really looks and studies these complexities, because these are the ones that are give us the information to adapt to a changing world. So thank you.
Great. Thank you so much. Thanks to both of you for that overview and some statement of some of the problems. And now Dennis is going to address some of those with a possible solution.
Okay, if I could have the charts, please. Folks yesterday said that we have to do something very different, and what you're going to see is very different. This is halophytes, salt plants, dry land plants grown on wastelands, deserts, using seawater irrigation with no desalinization to solve land, water, food, energy, and climate affordably and soon, all of it. There's two types of plants, glycophytes, which are freshwater plants. You look at the window, that's what you see. Then there's halophytes, saltwater plants, which have been utilized for food and fodder in India and other countries for hundreds of years, and now in 22 nations around the world for food and fodder. Just a goodly portion of the Sahara is capable, if we plowed it up and irrigated with the Mediterranean and grew halophytes with direct seawater irrigation, of producing sufficient biomass to replace all of the fossil carbon fuels, provide petrochemical feedstock for all the plastics, and all the food anybody wants to eat while returning much of the 68% of the fresh water we're now running out of for direct human use, i.e. solves land using wastelands and deserts, solves water because we're substituting salt water to grow food, solves food because we're growing food, solves energy because we're producing biomass at about biofuels at about $50 a barrel, and the climate because we're sequestering some 18% of the CO2 uptake in the deep roots. So conventional wisdom for agriculture is salt is bad, but if you plant halophytes, actually salt is good. The advantages of seawater ag, 97% of the water is seawater, we're not going to run out of it. Seawater contains a massive number of important minerals needed in the human diet, which we've just about depleted out of the farmland. And seawater contains 80% of the nutrients required for agriculture, and it's in a proximity to a large number of dry and desert areas. 44% of the land worldwide is wasteland. It has a lot of sunlight, and surprisingly enough, it has a lot of brackish saline groundwater. You don't have to pump ocean water. You can also pump saline groundwater. There's a Nubian aquifer in the eastern Sahara, which is absolutely huge, and we can utilize these to solve our problems. The characteristics of this wasteland halophyte seawater ag so far: no observable salt buildup, produces a cooler, moist surface, an unstable atmosphere which produces freshwater rain downwind. If we did this on the Sahara, you could put rainfall back in the Middle East and regrow the cedars of Lebanon, and also stop the desertification of the sub-Sahara. It utilizes what we have a plethora of, wastelands and seawater, to solve what we have now. There's about 10,000 natural halophytes, and 25% of the irrigated lands are now salt affected because the aquifers that we're now pumping, and it includes the Agua aquifer down in Texas and Oklahoma, are in fact becoming saline. The characteristics, the yields can be equal to glycophytes, and halophytes produce the entire product spectrum: seeds, fruits, roots, tubers, grains, foliage, wood, oils, berries, gums, resins, pulp, rich in energy, protein, and fats. There's a salt penalty, 35% more cheap salt water in order to grow this stuff. So you can use halophytes for food, fodder, biomass and energy, petrochemical feedstock, wood, CO2 sequestration, and wildlife habitat. For centuries on the Indian subcontinent, there's been a very successful saline brackish water agriculture for food and fodder with no salt buildup, and 22 nations are now growing halophytes for food and fodder. Sample wastelands for really massive capacity to do this: Western Australia, Persian Gulf, Arabian Sea, Middle East again, Sahara, Southwest US, including West Texas, and the Atacama in South America, and many others. The current efforts in the UAE, Boeing is growing halophytes for airplane fuel. I worked with the State Department. There's a halophyte operation down near Aswan. Farms in northern Mexico are also growing fuel, and then there's several others that are in the formative stages. So my last going off the stage chart is to utilize, the opportunity is utilizing wastelands and deserts, really inexpensive land, utilize seawater, which is extremely plentiful and inexpensive, grow halophytes, grow really massive amounts of food, massive amounts of biomass for both petrochemical feedstock and green fuels, while sequestering about 18% of the CO2 affordably with existing technology. Start now, 10 to 20 years out, you fixed land, water, food, energy, and climate. Thank you.
Great. Thank you. Thank you, Dennis. Thanks all three of you for those great presentations. Do we have questions? Yes, John.
The presumption across the panel, which I think we all share, is that certainly climate change is real. What I'm asking, my question is about application of your science to reality. Reality being that we have a gubernatorial election coming up in which one candidate says that climate change is the biggest hoax ever perpetrated, and the other, who claims to be a scientist, is saying the science is unclear. So my question to you all is, what can you do to affect the leadership in this state, and what can we do to help you? Because our governor claims to be a scientist and claims that there is no significant proof of anthropogenic caused climate change. It's just crazy. And I know your objectivity keeps you in a certain realm of being scientific, but there's too much at stake. We need advocacy, and we need to support that advocacy.
Let me start off.
Okay.
You heard yesterday that the climate change politics is driven largely by the financial aspects in the real world. And recently, the renewables are plunging through parity, and so the financial business is in fact becoming very successful. Half of the new generation worldwide is now renewables, and one of the previous speakers this morning went into this, okay? So it's actually not the concern about climate, I think, which is going to change things the way some of us would like to see it go. I think it's the favorable financial aspects which are just about here.
Dennis, you talked a little bit about other countries being involved with halophyte development. Do you see that in the U.S.? Do you see some attention to that now?
Huh?
In the U.S.?
Halophytes.
Halophyte?
Yeah, halophytes in the U.S. were actually started out of the University of Arizona. There's a major effort in the University of Delaware. DOE down at Oak Ridge has some halophyte work, and we are, becoming far more successful with this. The entrepreneur that actually started the major seawater farms operation in the Horn of Africa and is working now with United Arab Emirates came out of Arizona.
Okay. And Greg, you wanted to address John's question?
Well, yes, very quickly. I spent many years working diligently with politicians, and I woke up after a while that I was getting nowhere. And it's not because they're idiots, they're actually very smart people. They have an agenda, and their agenda is driven by two things. They're driven by the people in this room, and they're also driven by who actually gives them the money to get elected. And you have to just simply understand that. You can go and do all of the logical arguments you like. You are running up against that political reality. So a few years ago, we decided not to do that. And that's where, for example, the Rising Voices and the Engineering for Climate Extremes came out of. And let me just give you two examples of where that's now affecting the political process. Firstly, the last Rising Voices meeting, the Native Americans wrote directly into the presidential system saying, here is what has to happen. It's no longer me as a scientist talking about it, it's all the Indians in America and the Hawaiians in Hawaii that are doing that. That's what they listen to. And the second thing is that the financial industry gets a bad rap, and deservedly so in many cases, but the insurance and the financial industry, again, working with people like us, have actually come to a United Nations agreement. We're starting next year, every company in the US and other parts of the world that has shareholders, in other words, publicly listed, has to put in their sensitivity and their problems that they may have with climate change and with severe weather and similar things that come out of it. The world is moving in that direction, not because the politicians are taking us that way, because the people that elect the politicians are taking us that way.
And so let me just add to the conversation a little bit about voices. I mean, our voices as scientists are a small percentage of the population. It's your voices that have to come through. And let me just tell you a little bit about Massachusetts. So maybe you can actually concretely tell your gubernatorial people, look at what's happening in Massachusetts. So in Massachusetts, there has been a very concerted effort to put in place an agenda for a green economy, a green and blue economy. The governor has done it, the state legislature has done it, there's resources that have been put into investments that have been done, and we're getting to see results already in terms of economic development. And this is where you have to talk about it in terms of financial terms. You have to talk about it in terms of human terms. You have to talk, that's the way. You don't talk about it in terms of science terms. There are things that are happening here in Colorado that shows that the climate is changing, okay? The anthropogenic forcing, regardless of if you believe in anthropogenic forcing or not, the climate is changing. And we do have to get away from this business of basically just talking at the scientific level and instead casting it in terms of economic development, human stories, and basically what's happening to the environment as a whole. So Massachusetts has had some success stories in a period of 5 years. Okay, it's only been 5 years when they've been doing this. So take a look at it. Go on the website. Talk to people there. I've been on their committee, so you can talk to me later.
Another question. Yes.
A question for Mr. Bushnell. Halophytes sound too good to be true. Many of the Middle Eastern countries that would struggle with food have lots of money. Why does the list not show Saudi Arabia, for example? It sounds too good to be true. It convinced me that it's not.
I have worked with the Saudis. The Saudis called me up and said they're worried after they run out of oil, what's their economy going to be? And I've worked with the people in the province of Alberta for the same reason. And I asked them whether they had any sand, and they allowed they had sand. And I asked them whether they had seawater, and they allowed they had seawater. And I said, have I got a deal for you? And the last time I saw, the Saudis were going down the street looking into halophytes. When I said the Middle East was on my chart, okay, that's one of the major areas, again, for energy.
Okay. One more question. Yes.
Hello, my name is Stephen Hoffman. I'm really honored to be here. I live in Boulder. I work in natural and organic foods, and I'm also working on the Colorado ballot initiative to label GMO foods in our state. I was very curious when you brought up the dead zone, because the dead zone is actually caused by agriculture driven by genetic engineering, and it's all that synthetic nitrate fertilizer that actually just poisoned the water of Toledo, Ohio. So call that a dead zone too, because that's an algae bloom. And it's caused by GMO agriculture. We think that GMO agriculture and conventional agriculture in general contributes 30% of the greenhouse gases to global warming. Interestingly enough, and I'm very interested in your halophyte conversation, because according to Rodale Institute, organic food and farming actually puts so much carbon back into healthy living organic soils that it can actually sequester more carbon than is being released in our atmosphere. So there actually are open source, low cost solutions to sequestering carbon, and it has to do with agriculture. Agriculture as we practice it today, which is why we want to label GMOs, is because that agriculture has killed the soils, releasing all the carbon into the atmosphere, and is really contributing to climate change. Thank you very much.
Okay. Okay, one more question. You're pointing over. I can't see. Okay. Behind the podium.
Is it on? Oh, okay. We were at, I'm with Chief Looking Horse, and we work on world peace and purity and a lot of the issues that are going on internationally. And I wanted to ask about, as scientists that you are, what is your thoughts on Fukushima, and how come the governments don't tell the truth? And I'm talking even about the UN, the effects of what's going on with Fukushima, what's going on in the Pacific Ocean, the death that's occurring. Why doesn't that knowledge ever come out to the mainstream public of how it's affecting us now and how that's affecting global warming?
Anybody want to take that? It's a little out of everyone's area.
I'll take it in a different context, but I think Susan wanted to say something.
I'll talk about Fukushima only in the context of the radioactive release into the ocean that's associated with that. And there has been, I mean, if you really want some really good concrete information, very straightforward evidence-based information, go to our website and look at the Center for Marine Environmental Radioactivity that's just been published. We have a scientist who immediately when the tsunami hit and when the meltdown of Fukushima happened, realized that this was probably the largest accidental release of radionuclides into the ocean. We worked very hard with him, and it wasn't through the governments or anything that we got funding to get into Japanese waters and off of Japan waters to be tracing these radionuclides. And basically, who came to the rescue for that funding was a private foundation. It was the Betty and Gordon Moore Foundation. One of the first things you have to do in scientific evidence of what's happening in some of these crises is to get the baseline data. So that enabled to get the baseline data and also to establish relationships between Japan and other international scientists to really pull together in a cooperative way to begin to continue to trace what was happening with the Fukushima ocean radioactivity. I can't tell you all of it, but they have also, these scientists have worked very, very hard in getting information out to the Japanese public. And in fact, there was a workshop and a public forum. The Japanese came in droves and thanked the scientists basically for really getting the unbiased, solid information out there. The West Coast threat, people kept on worrying on the West Coast, were very worried about the plumes of radioactivity that might come onto the West Coast. We worked very creatively through crowdsourcing to get, again, samples of water along the West Coast, and that has come in to be analyzed, and it basically shows that the level of threat is very, very low, and if it's well below safety standards. But if you really want the information, go to the Woods Hole Oceanographic Institution website. We have a whole article on it and a whole center devoted to it.
I want to thank all of you for your interest this morning in this panel, and please join me in thanking these distinguished scientists for their time.